Hey everyone, welcome to Fine Tuning series episode number 1. Today we'll be dealing with a BERT model and we'll be fine tuning it for a NER use case. Firstly, what is NER? Hi Deepthi, can you throw
Right.
some light on what is an NER use case?
Sure. So NER full form is name entity recognition. Okay. So let's say you have a text. Each and every word in a text resembles something like some entity. It refers to some entity. Let's say you have an address. So there can be multiple entities in an address like house number, street name, pin code, state, city, or district. Right. So there can be multiple entities in a statement. Let's say you have a paragraph and then you wanted to extract some organization names from the paragraph, or some human or person names from the paragraph. So those can be entities. Let's say you have this kind of use case, then we can pick a base model, mostly but variations of BERT model, and then you can fine tune for your particular NER use case. So that's actually the name entity recognition. Basically, we're trying to extract the entities from the text we have.
Okay, so should we go ahead with the use case implementation?
Sure, sure. Just sharing my screen quickly. Is my screen visible?
Yeah,
Yes. So let's start with the fine tuning part. So first part is creating the data set. Okay.
so
So we
what is
have
the data set that we are using?
Yeah. So here I have picked a very kind of a toy data set that I have created. So this might
Mm-hmm.
not be the real world data set, but it depends. Like if you have a data set, you can accordingly create your data set in this format. So if you see on the right side, there are two columns. One is the token, other one is the NER tag, right? So if you
Mm-hmm.
see each record, so first you need to tokenize your entire statement, whatever text you have, into words, and then you need to refer those words to your corresponding entities. So
Okay.
entities will be in terms of numbers. So you can just put a mapping. So here I've taken a very toy data set, and then so one I'm referring to the fruits. So I guess it's zero, right? 2 and 3. Okay. So 0, I refer to the fruits. 1, I refer to the vegetables. And 2 refers to animals. And 3 refers to all. All is nothing but the rest. Okay. The rest I'm considering it as others. So let's say, for example, I have a statement, the lion finds a tiger. Okay. Like very basic. So the finds a all are other than fruits, vegetables, animals. So I've marked it as 3, corresponding numbers as 3. And lion is an animal, so I've put it as 2. And tiger is an animal, I've put it as 2. Okay. Similarly, if you see here is a mango, and then I've marked it as 0. So because it's a fruit. So
Okay.
that's how we need to prepare our data set. So make sure whenever you are trying to fine tune for an NER use case, it's very important your data set has to be pre-processed, and then you need to put it in this particular format. 2 columns, token, and the NER tag.
Okay. So, what is the length size of the data set?
So here the data set size is 200. I've taken a smaller one comparatively,
Oh,
but
is it possible to train with such a small data set like this?
yeah, it's okay. Like you can give it a this, since this is a toy data set I've taken as 200,
Mhm.
but it's always good to have a larger data set whenever you're fine tuning a BERT model. So it's better
Okay.
like kind of 20K records if you have, that will help. And it also depends on the number of classes you have. So here, if you see, I have 4 classes, right?
Hmm.
So lesser number of data also works, but if you have large number of classes, then comparatively you need to have a larger data because it has to
Yeah,
find patterns for
exactly.
all of them. Kind of it's a
Hmm.
classification problem, right? So try to get it at least like 40K, 20, above 20K records. If you have, you'll get a better accuracy. Also, it will be in a generalized way.
Okay.
Instead of getting overfitted, you'll have get it in a generalized way. So better to
Okay.
always have a larger data set, I say, especially for fine tuning BERT models greater than 20K
Hmm.
records.
Yeah, got it.
So now let's have this. Let me load this data set. So as you know, as you load the data set, like I have the list. I've created a list and then saved it. But when you read it, it will not come as a list. It will come as a string.
Okay.
If you see here. right? So this comes as a string. So now you need to convert it into list, and then that you can do it using ast.literalEval. So this is a function that would convert your strings to proper lists. This list kind of strings to proper lists, and also like JSON strings gets converted to proper JSON. So this is the functioning of the uh, literal eval. And so once we are done with it, then we'll get a proper lists.
Okay.
So now let's split our dataset into three parts: train, test, and validation.
Mm-hmm.
Okay.
So what is the difference between validation and test?
Yes. So train, as you know, it's very simple. We are training on that data.
Yeah,
Very clear.
it's the training
But
data.
always, people have confusion between validation dataset and test dataset. So
Yes.
basically, validation dataset is the one where we use that dataset to fine tune, to do the hyperparameter tuning. So we use
Okay.
train dataset for training the model, but we use validation dataset for hyperparameter tuning. That means still the model have seen this data
Mm-hmm.
for hyperparameter tuning, not for the training. But test dataset is completely out of sample. That means the model haven't looked at this data itself. It's
Yeah.
completely out of sample. That's called the test dataset. So we
Okay.
use train dataset and validation dataset for completely building our model, even after like
Mm-hmm.
fine-tuning our hyperparameters. But finally, we test it on test data for the evaluation purpose, so that the model haven't seen the data yet.
Mm-hmm.
So as you know, the model selection, we have a test train split. So initially, just I wanted to take I want to first split this into test data set and the others. Like I'm taking the last 10 records as the test data set, and rest all I'm considering for the entire train and the validation. And then I'm
Okay.
taking the point 2 as the split. That means 80% of train data, and then 20% is for the validation. So these are the numbers that I finally have. Okay. Let me run it as well. Yes. So now let's start with fine-tuning activity. So we have prepared our model, prepared our dataset. So dataset preparation is the major part, because in the real world, datasets will not be very clean. So you will have to clean it and properly create your dataset. So now your 70% of work is done preparing the
Oh,
dataset.
okay. That's
Rest
interesting.
Ah, so when you come to the real world, 70% of the works goes in preparing your data set itself, because you need to have a good accuracy, right? Like 100% accuracy on your NER labels. You cannot randomly put some numbers. It has to be accurate. So it will take some time over there. So next is the fine tuning activity. First and foremost, we need to choose a base model for the fine tuning. So I
Okay.
have chosen modern BERT over here. Modern BERT
Oh,
large.
is there a reason you preferred modern BERT to BERT?
Yeah, so I know a lot of people might know BERT model, and there are a lot of variations of BERT model as well, like Albert, Roberta, then again modern BERT. So
Distil
there is a
BERT.
reason why, this still BERT. So there are reasons why I have chosen modern BERT. One major reason is the context length. So if you see, BERT model has 512 context length, like 512 tokens as a context
Okay.
length, which is very less. So that can take maximum up to 512 tokens alone. But this modern BERT has context length up to 8,000 tokens, 8192 tokens. So which is
Mm-hmm.
comparatively much larger,
Yeah, it's way higher.
way high.
And
That's the one main reason, so that now you will be able to use larger strings in that particular record. Like
so
you
what
need not be,
about the speed? I mean, like with large context length, will the speed reduce or we have something for the speed as well?
yeah, no, no. If the speed is not reducing, they have actually made it faster compared to the BERT. It is
Oh,
five
wow.
times faster than BERT. Even
Okay.
though the context length is higher, even though the number of trainable parameters are slightly higher, it's actually 340 million for BERT, and it's 395 million for this modern BERT large. Even though there is slight increase, but still the computation is faster. The reason is
Okay.
that I'll show you there's a collate function that we're going to use, that is dynamic padding that we are doing, because of which a lot of computation has reduced. And there are a lot of activation. There's another variety of activation function and attention, flash attention mechanism that they have used for the efficient inference and for efficient long inputs as well. So these two are the major parts that would help us keeping it faster.
Mhm.
Also, when it comes to performance wise, like the accuracy, it has outperformed Roberta and BERT as well. Because of this, there are one important rotatory positional embeddings. This is what which helped improve the accuracy. Uh,
Mhm.
in BERT, you know, right, there is only positional embedding, not the rotatory
Yeah.
positional embeddings. So let's not go very deep into this, like what are the improvements in it, like how it's getting improved, maybe the background architecture or the background mathematics. We'll take it in another video. But now what you need to understand is modern BERT is much better compared to the BERT in terms of context length, in terms of processing speed, in terms of performance, in terms of memory requirements. So it's way better than BERT. So that's the reason we are choosing modern BERT as a base model,
Okay. Okay.
right? So yeah, these are the, so whenever you're choosing a model, try to understand what are the various, what is the size of the model. Let's say if you're using the base one, then it's 149 million parameters. If you're using the large, then it's 395 million parameters. Since I am okay, like as you know, like the number of parameters increases, it means your model accuracy keeps increasing. That's generally true. So I'm okay to take 395 million parameters because it takes around 2 GB memory, and I'm okay with it since I'm using Collab. It gives us 16 GB memory, right? So I'm okay with it.
Mhm.
So that's the reason I'm picking modern BERT large itself instead of base. And also
Okay.
one more thing is the data on which this modern BERT is trained, it is much larger, and also it is trained on code data, codes.
Oh.
So that's why if you have a use case, like say you wanted to extract some entities from code, let's say the variable names or the function names from the code, this kind of use case, if you have, then it's good if you go with modern BERT. BERT is not trained on the code, but this is extensively trained on code, so it will help. So always try to go with modern, but only it has a lot of advantages over normal BERT. Okay. So when you go to files and versions, you'll be able to see the size. So here, if you see the model tensors. So this is actually base model. Let's go to the large model, files and versions. So this is various files. So see around 1.5 GB it takes. So this is the final model file. And you have to remember that like whatever model you fetch it from Hugging Face, there are three main files that you need to check for. One is the model.safe tensors. The other one is this config file, which contains all the architecture information, and then the
Mhm.
tokenizer. These three are important. These three are the ones that we are going to load it for using the model.
Yeah.
Okay. So now we have selected our model. We are done with it, and now loading it
Mhm.
is way easier. So we have Hugging Faces. So we have this auto tokenizer and auto model for token classifier for loading the model. So first we'll have to load the tokenizer. Auto tokenizer from pre-trained, and you need to put your name of the model that you want to load. So you can get the name from here. If you click, okay, you can actually just copy from here itself. This is the model name. Or if you wanted to code, then you can pick it from here as well. So with this, you'll be able to load it directly.
Yeah.
Okay. So try to use this model, and then just paste this, or you'll also have description over here, like how to load it and all. Okay.
Okay.
So next, so now we have loaded the tokenizer, and then we have loaded the model as well. So here there is one parameter that you need to define, the number of labels. So
Labels. So
you
this will have to modify according to our use case, correct?
exactly, yes. So it depends on the number of classes that you have. So here I have four classes, right? Fruits, vegetables,
Yeah.
animals. Last one is others. So I have put four. So this you have to change it accordingly. So let me load the model. Also, this particular code will help you check whether GPU is available or not. So if you're using a collab, then you can switch from CPU to GPU. Okay, we'll just run and say I haven't run it. Let me run now. Post this. This will take some time. So if you see here, so all the tokenizer config, tokenizer, there are a lot of special token mapping as well, config file. Model tensors is the largest file we have seen, that 1.5 GB. So it will take some time for loading, and then we'll be done. Yes, we are done. So now let's check if we have GPU available. So the GPU is available. We are already running the GPU. If you check here, uh, just click on it, you can see. So our RAM is like 12.7 GB we have, and then GPU RAM we haven't used it yet. So this number you can check it over here. Okay. Fine. So we have loaded the model and our GPU is also running. And then next is, so we have prepared a data set this way, but this cannot go as the input to the model, the modern BERT model. So this requires some modifications. What do you think the modifications should be?
Okay, so it has to be sent in as a sentence.
No, it cannot. We cannot send it as a sentence. Ideally, we'll have to tokenize this further. So right
Okay,
now, we
yeah,
have
yeah,
put it into words, right? So we'll
yeah,
have to
I got
tokenize
it.
this further in order to send it to the model. So that's what we are exactly doing it over here. We are converting our inputs so that these are these can, I mean, we have to convert it into a format such a way that model can take it as the input. So model can take
Okay,
only the
yeah, yeah,
token, right? Not the
yeah.
sentence or not the list of words. It has
Words.
to be further splitted using the tokenizer. So now,
Okay, yeah,
first,
I got it.
we have a train dataset, test dataset, and the validation dataset.
Mm-hmm.
So now we have just converted this into the dataset format. So this is the format, Hugging Face format, Hugging Face dataset that we need to use for further training. So I have converted right now. I have it in a pandas data frame. So that I have converted all the train test and validation datasets have converted. So now
Okay,
I have to tokenize this and then map it to its corresponding NER label. So let me show you an example, okay? So that would help you understand better. So let's say we have this tokenizer. So second, yeah, second. Hmm. So if you see, this is the first statement that I've picked. The lion finds a tiger. Okay. So this is a tokenizer function that would tokenize this. Let me run this. Yes. So this is being tokenized further. So CLS is the starting tag and SCP is the ending tag. Okay. And the rest, if you see the lion find has split it into find and S, two tokens.
yeah,
And A remains same and tiger gets split to T and IGR, two
IG, yeah.
tokens. IGR, right? So this gets further splitted. That's very important. So this initially we have in this format, but finally we have to convert it into this format and its corresponding labels as well. For example, if you see, we have these NER labels, right? But if you see the length is 1, 2, 3, 4, 5, just 5.
Yeah.
But after splitting, our length of list is much higher. So let's say tiger has is corresponding to label 2, but now it has split into two tokens. So now the last two values, these two tokens has to be mapped to 2. So
Two,
that
yeah.
corresponding labeling also needs to be done, right?
Yes.
Mm. So one more important point that I want to make here is, if you see, a tokenizer function can take input in two forms. One is the sentence, other is the list of words. It can take
Yeah.
in two. Let's say if it takes list of words, this will be the output that you have seen. Let's say the same thing. Okay. Let's say if it is taking as a sentence, let's see what will be the output.
Oh, the tokens are different now. And I
Yes.
think it isn't, it is detecting like if there is a space, it's adding a G like character before the word, and
Mm,
also the tokens are different. So the
correct.
same sentence is being tokenized differently.
Yes. So you have to be very, very careful here. This is the common mistake that people make. So while tokenizing, like while training your data set, they use this as the format, like the list of words as the input as the format. But later on, while the evaluation, they directly send the sentence. So that's where their accuracy will drop. Which are because
Yeah.
the data is trained on T and IGR token. But now
Mm-hmm.
you're sending Tiger as a token. Surely it can make mistakes, right? Possibility of making mistakes is much higher.
Yes, exactly.
So keep in mind that while training, since we are sending the input as list of words, even while evaluation, try to tokenize it based on space. Like you might have created this data set, right? With maybe you might
Yeah.
have to with space or comma or some special characters. The same pre-processing logic try to apply it while evaluation as well, so
Okay.
that your tokens will remain same and you'll have a much better accuracy. A lot of like
Mm-hmm.
I have trained a model for the address parser, and then with this change, okay, initially I was directly sending the entire statement and my accuracy was around like say 70% only. But then when I realized this was the mistake and when I changed it, it got increased to 90%. Lot of
Oh, okay. So the format that we use for evaluation plays a lot of role in getting the accuracy.
Yes, so your input format and output evaluation format has to be same. Only then you'll have a good accuracy.
Okay.
Okay, next. So once you tokenize it, and then so this is the entire function that I've used. Yeah, I'll just enter it. So yeah, this is the entire function. Uh, this tokenizer, and then this tokenizer will give me three outputs. One is this words and its corresponding input ID. So this actually I've converted these tokens into IDs so that I wanted to show you how the IDs look like. So these are the various IDs corresponding to each token. So finally, the input to the model will be the input IDs, not the text. You know, right? For
Yeah.
any NLP use case, model can understand only numbers. It cannot understand strings or letters. Okay, we understand only a number. I mean the letters, not the numbers. So there has to be some transition. So we understand letters, so we give the input as letters, but later on internally it will convert it into numbers and take it as an input so that it can train. So that's the transition that is happening. So these tokens are being converted into numbers.
Okay.
Okay, it's understanding. So there's
So
one
what
more thing.
is the attention mask?
Yeah, I'm about to say that. So attention mask is the one. If you are aware of BERT model, it's an encoder model, right? If you see in the encoder model, we make use of all the words because the input will make use of entire input. But if you see in the decoder model, you will have to mask few words because we
Yeah.
don't know the next word, right? While predicting for the next word, we are not aware what the next word is, so we'll mask the next words. We'll only retain the current word, and the next word needs to be masked. But
Yeah.
here, since this is a encoder model, we need not mask anything. Entirely will be an input. So these are basically the mask. That means if one, that means we are not masking it.
Masking anything.
Yeah, we are not masking any of these words. That's what it means. Yes. So next is one more major part that is happening in this part is if you see here the first token that is the start and end. So this is a kind of classification problem. We're just trying to like label each of the token to a particular class. So the start token and end token, we don't need to train it on start and end tokens because that doesn't make any sense for us to label it, right? And we're not trying to identify the start token and end token as well because we're giving the entire statement. So these two shouldn't be calculated in during the loss calculation. So we'll be calculating the
Okay.
loss, right? So at that point of time, we shouldn't calculate this first and the last values, these tokens. That needs
Okay.
to be eliminated, else it's actually wrong, right? Because we're not training on this. So that's what we're doing it over here. We are adding -100 to these labels, the first one, then the last one, so that model understands that I shouldn't train on these two tokens. I can ignore these tokens. That's what it understands.
So you're giving it insanely large token number. Like for the
Hmm.
others, it's 0, 1, 2, or 3, but for the starting and ending token, it's -100.
So since we are keeping it uniform, it understands that it has, and no, there is, you can actually put another number also. I'll tell you where we are doing this. Like while doing the loss, while calculating the loss, we are ignoring if it is -100.
Mm-hmm.
Yeah, another number, like you can put -120 as well. But in the later, while during the training part, you'll have to mention that if the number is -120, we'll not add it up for the loss function. We'll
Okay.
ignore it. You can put any number. So this is what is actually happening it over here. So we are tokenizing it and then doing the mapping, putting the label mapping. So it's the same thing. I'm doing it on all the data, tokenized data, I mean the train data, test data, and validation data. Okay, now on all of this I'm doing. Now you'll have this dot, this, what
Data
is data
collator.
collator, right?
So is this the thing for dynamic padding?
Yes, exactly. So let's say, right, the input context is only 8,000 tokens. We cannot take
Yeah.
more than. One more thing you need to remember is, in case your input is more than 8,000 tokens, then what you
Mm-hmm.
should do?
You'll truncate it on
Hmm.
either side or
Exactly. You can either truncate it from the head or you can either truncate it from the tail. Either
yeah.
of them you'll have to do. So if you don't do it, then it will throw an error. It will say that your input token is out of, like, larger than the context, and it will throw an error. So you have to mention, initially itself you will have to either truncate it from the head or from the tail and give only the 8,000 tokens, right?
Mm-hmm.
So let's say I have an entire data set. So generally the input length has to be same for any model. So let's
Mm-hmm.
say, so one, two, three, four, five. Let's say I have here five and here I have four words. Okay, now I need to pad this. So
Yeah.
the input has to be of same length.
Yeah.
So since I have only four, I need to add one more there. I'll just put zero. It's like a padding. It's not
Yeah.
a meaningful one. It's just padding, kind of some random word just to make it uniform. That's it.
Okay.
Hmm. So let's say I have a large data set, and then most of the words are of five words only. Okay, let's say
Mm-hmm.
five tokens. There is only, like, say, 10% of the cases where I have 20, like 30 tokens. Okay,
Okay. So that will
ideally,
definitely increase the memory size, right?
yes, not even memory, computation wise also it will be very higher,
Mm-hmm.
right? So instead of, let's say, ideally we have to pick the longest one. That means the 20 tokens, and we will have to pad all of them to 20 tokens, list of
Yeah.
20, right? But if we do that, there's too much of space, unnecessary computation. It's of no use. Ideally,
Yeah.
parent of no use. So that's why, instead of doing entirely padding on the entire data set, we do dynamic padding. That means we take a batch. We don't actually train it on the entire data set at once, because it's too much of memory consumption, right? So we
Yeah.
take batches. So we take, let's say, 10 batch of size 10. I have taken 10 records, and then I'll check the what is the highest of all, what is the maximum number of tokens present in those
Mm-hmm.
10, and then it would be mostly 5 only, because there are only
Okay.
few things where we had 20. So only for few batches we'll have to pad it till 20, but for 90% of the cases you'll have to just pad it till 5. That's it.
Mm-hmm.
So that's a dynamic padding. That means padding happens based on the batch instead of entire. So you'll take the highest of that particular batch, the number of maximum tokens for that particular batch, and pad it accordingly. That's it.
Okay. Yeah.
So this is one of the main reason for why it is 4 times faster than BERT. This is one of the reasons.
Oh, okay. Yeah. Got
So
it.
this is done. So once we do the collate and once we collate the input, then okay, this is just an input. Then I'm just printing how the dataset look like once we are done. Like, so this is the dataset format. This is like Hugging Face dataset that we are using over here, which is compatible with the Hugging Face trainer function. Okay. So yeah. So if you see, I've just printed one value from this tokenized dataset train. So these are the tokens that we have given, and then these are the NER labels that we have given as the input, and then it has calculated, it has tokenized it, and these are the corresponding input IDs for it. So it doesn't see, as I said, model doesn't need letters, just need numbers. So input IDs is what is required, and then detection mask I've mentioned, then the labels, the corresponding labels as well. So if you see this -100, the first and the last one, which needs to be
Yeah.
ignored. This is how it looks. So the entire data set looks like this. This is one particular sample. Okay. So next is this. Okay, this is a very. It's always important to check the class distribution of your data. Let's say your data is imbalanced, then there might be a problem. Let's say I have four classes, right? And then if you see two classes are of very high number and other two are very low.
Yeah.
So
It's an
this is always
imbalanced thing.
this is an imbalanced one. This is always not good. Always try to keep your data set balanced. This will have a problem in for the model to understand. If you see, the two is the animal, right? 0 and 1 are the fruits and vegetables. So
Vegetables.
now it won't be able to give you better results for fruits and vegetables because the sample is very less. And
Yeah.
animal it will give to some extent. And others we can't avoid, that we can ignore. But at least others, if you try to improve it, it's better. So this is just to check. It's just a basic check. You can just run it and see what is the distribution of your classes. And then in case you wanted to do some data augmentation, you can do it.
Yeah.
From transformers, next is this training part. So
Yeah.
there are two most important parts whenever you are building a model from scratch or you are fine tuning any model for some use case, any use case it could. There are two most important parts that you need to remember. One is the loss function and the other one optimizer. So what loss function you're using or what optimizer you're using plays a very vital role in building the model.
Okay.
Okay. So let me explain what is the loss function and the optimizer that we are using for this NER use case.
Mm-hmm.
So first is a loss function. Okay. Do
So
you know
this
what?
is the cross entropy loss.
Yes,
Is it?
yes, exactly. You identified it. It's a cross entropy. And for example, let's say I have one entity that is lion. So I have predicted these values. So zero point 0.1 probability for fruits, 0.02 for vegetables, zero point 0.8 for animal, and 0.08 for the others. Right? So these are the
Yeah.
prediction probabilities that I've got. Let's say issue, and this is actual one. So
Mm-hmm.
actual one is in the place of animal place, and rest all are zeros.
Yeah.
Let's say this is your value. So my loss function here means that it's minus sigma. T of S is nothing but the probability of true
Okay.
probability dot log of uh, predicted probability.
Mm-hmm.
So here basically what it's trying to say is we are trying to check how close your predicted probability distribution is with the true probability distribution. That's actually
Yeah.
called the cross entropy. So if it's very close, then we are good. If it's far apart, then we'll have to bring it close by
Yeah.
training. So if you see based on these values, what will be the value, final output value? So we are just multiplying this zero point 0.1 with zero, I mean log zero, and then sorry, zero into log of zero point 0.1, and then zero plus zero into log of 0.02 plus one into
1 into
8.
log point 0.8. So only that term will remain.
Yes, since rest all are zero, the only one term will remain over here. Since so 1 into log of 0.8, since it's a less than 1, so the value would be negative. So that's why there's a negative over here. That's a balancing one, which makes it positive overall. So we
Yeah.
are trying to reduce this value. So let's say if finally we want to achieve that, this has to be 1. So if we change this to 1, what will be the entire value of this loss function?
It will be 0.
0, exactly. So log 1 will become 0. It means that we are trying to reduce this loss function to minimum, that is 0. That's the
Yeah.
target.
Yeah.
Yes.
Okay.
So this is the
So
loss
what is the
function.
optimizer that we are using here?
Mhm. So what is the, first of all, what is optimizer? So the purpose of optimizer is to identify the proper parameters. Let's say you have a lot of trainable parameters in your data. So you do not know what values you want to put for those weights, right?
Yeah.
So optimizer work is to finally find out the proper values for these weights such that you have your least value for your loss function.
Loss
So
function.
it's trying to reduce, it tries to optimize your loss function, tries to make your
Yeah.
loss as small as possible, making your like assigning proper weights to your parameters.
Hmm.
So the optimizer that is being used for this use case is Adam W. So this is the
Okay.
optimizer that is being used. So I think a lot of people might have heard about Adam, right?
Yeah.
Might have
Yeah.
heard. Huh. So now
It's
let's see like what is the difference between Adam and Adam W. Okay.
okay.
So these are the four things. So one is this MD. Okay, Adam is the combination of momentum and RMS prop.
RMS prop.
Yeah. So momentum is nothing but the weighted average of previous momentum and the current gradient.
Yeah.
And this is RMS prop. So here, this is the weighted average of the previous RMS prop and the
Hmm.
square gradients.
Yeah.
Gradient square.
So
Mhm.
that will take care of the adaptive learning rate. Correct.
Yes.
RMS prop.
Yeah, this will take care of your adaptive learning rate, and then MT momentum will take care of faster convergence. It will speed up
Yeah.
your convergence.
Hmm.
So the combination of these two is nothing but the Adam. So there is
Yeah.
one bias correction also that is being done over here, because in the initial stages, your MT and VT values will be very low, like it will be close to 0.
Hmm.
Okay.
Yeah. Yeah.
Since it's very close to 0, we might have bias towards 0. That's why we are doing some bias correction so that that bias is removed. So that
Okay.
bias is MT by 1 minus beta 1 power T.
Okay.
So
Yeah.
this is the bias correction that we are doing, and this is the momentum, this is the RMS curve, this is the bias correction. So
Okay.
finally, if we put everything together, the final Adam formula is this. This is how we update. We try to find out what is the next set of parameters that we want to try, so that
Oh,
our loss function is reduced. So theta t plus 1 is equal to theta t, the old one, minus eta is nothing but the learning rate
learning
into,
rate.
this is the momentum
Yeah.
divided by root Vt. Vt is nothing but the RMS prop plus epsilon. Epsilon, we are just putting it because let's say V hat is 0, then we might get zero division error, right? Just to
Yeah.
avoid it, we're just putting epsilon. So that epsilon will be like very small number, like 10 to the power minus 8, something of that sort. Very small number, just to avoid zero division error while computation.
Okay. Okay.
Okay. And this beta 1, beta 2 are the weights. So this will be around like beta generally some zero point 0.9 around you can put. And beta 2, this is the, like beta 1 is nothing but the weightage that you want to give for your older momentum. So you
Hmm.
can control it, but generally we put it zero point 0.9. And beta 2 is the weightage that you want to give for the old RMS prop. So that is
Okay.
around like 0.98, 0.99 you can put. Okay.
Okay.
So yeah, so this is the formula for Adam, and
Hmm.
this is the formula for Adam W. So if you
Okay.
see, what do you see the difference?
I mean, like here, the loss function got modified with adaptive learning rate
Mm.
and the lambda plus 2 plus theta. And
Mm.
here, directly the gradient update step has added the term.
Huh. So here, if you see, there is one difference, major difference between Adam and Adam W. W we mean by weight. Okay, it's actually Adam W is nothing but Adam decoupled with a weight
Wait,
decay.
okay.
So that weight decay is nothing but this lambda. Okay, lambda into theta t. Theta t is nothing but the number of parameters. So in Adam also there is a weight decay term, but it is present in the loss function. So
Mm-hmm.
we add this decay along with via the L2 regularization, that is theta square, this mod theta, right? So that is L2 regularization. So we add this weight decay via L2 regularization to the loss function in the Adam.
Okay. Mm.
Okay,
Yeah.
because of this, it will hinder with our optimization process. So this will make our gradients change, and that will impact our adaptive learning rates. So,
Yeah.
which is a drawback of this Adam, because of which it might overfit us sometimes for the complex models. It might overfit, and also it might become slower as well later on. Initially, it might be faster, but as you go, it might become slower in terms of converging.
Mm-hmm.
That's why they have put another variation of Adam W where adding this decay, this particular weight, they're doing it in the doing while updating the parameter values. Instead of
Okay.
adding it in the loss function, we are adding it in the parameters. Like so, here if you see, this is not uh, it is not. Creating any hindrance with the optimization process or the learning adaptive rates, because learning adaptive rates, that is root we had, is already being calculated without this value, and then later on we are adding this weight,
Okay. Yeah.
that's the
Got you.
decay weight, right? So that's why this is a better, this becomes consistent, this becomes very consistent, and the optimization process goes smooth. So with
Mm-hmm.
this Adam W, you'll not I mean, you can generalize it better. You won't overfit. You generalize it better. You regularize it better, and also it is faster. Initially, it might be a bit slower, but later on it becomes very fast, and you can generalize it better. It's always
Yeah.
good to use Adam W as your optimizer compared to Adam. Adam has disadvantages. Okay.
Okay.
So the optimizer that we are using is Adam W. Loss function we are using is cross entropy. Clear?
Cross intro. Yeah. Okay.
Okay. So let's continue. We have looked into the loss function and the optimizer that we're using for this for building this NER model. And now it's time to look into other parameters. So if these are
Mm-hmm.
the various parameters that you can define. One is the learning rate. So you have seen learning rate in the formula, right? This is the learning rate eta. So
Yeah.
that is the value that you can define. You can just put this number 2 into e power minus 5. It's generally, it's always good to put learning rate to be smaller, so that you'll take smaller steps,
Mm-hmm.
right? It's always good to take smaller steps. If you're
Yeah.
taking large, then you might
You
miss
might
the
miss out on the gradients.
correct. You'll miss the minima, and then you'll keep oscillating near the minima. So it's
Mm-hmm.
good to put a lesser value. Then per device train batch size. So batch size is depends on your memory requirement or the computation power that you're running, like if it's a GPU or what is the memory that you have.
Yeah.
So here I put it as 30. You can, let's say, you have larger data like 50K, 60K samples. Then
Mm-hmm.
you can keep it bit higher also, because else it will take I mean, it's always good to put, if you put lower, it means that you need to compromise on some accuracy. As
Yeah.
high as this value, as high the value is, so the accuracy is that high. So it's
Yeah.
actually the
So
best.
the gradient will get updated once in every 30 samples, right?
Exactly.
So
So batch sizes, yes. If you're keeping your higher value, then it look at larger sample and then updates the parameters, which is actually accurate compared to the smaller one. So, but
yeah,
based on the memory requirements that you have, you'll have to define this, or else you'll get memory exhaustion error. So
yeah.
just make sure, try put it like 30 or some cases 100 also works. Depends on the size of the machine you have. And then the number of training epochs. Okay, what is an epoch?
So epoch is running. If it is called one epoch, if the data is trained, entire data is trained for one time, and the gradients updates are done for every batch. But yeah, after it's the data has been trained once, the entire training data set.
So yes, the epoch, one epoch means one pass over the entire training data.
Yeah.
So one pass over the entire training data is called an epoch. So here we have put as 10 epochs. So if you see our data set train is around like 150 samples, right? So 30 is
Mhm.
at batch. So for each epoch, I think 150 by 30, like 5 steps you will have roughly. So for each epoch, 5 steps.
And then total 10
Total 10.
epochs, so 50 in total.
Yes, 50 steps you'll have. So next is weight decay. Weight decay, you remember, right? Adam W,
The
the weight lambda is
lambda.
nothing but the weight decay. Generally, they put either 0.01 or 0.02. You can put
Hmm.
it in. So next is just to save. Logging steps is nothing but just to, save your learning loss values for every
Hmm.
2 steps.
Yeah.
Or if you put it higher, it will be saving your evaluation metrics uh, and the loss values for every so and so steps.
Okay.
So yes, so these are the various parameters that we defined. And there is a trainer module present in the Hugging Face itself. So in order to use this function, you need to have an API key for Hugging Face. You'll have to log in and get the API key, because when you run it, it asks for an API key. If you don't have it, then you won't be able to run. Like for example, when you're running it, training access missing. Just a second. Let me run this. So see, it's asking for an API key, but I don't have it right now. So if you have it, you can put it and then run, and you'll be able to run it. So here, if you see the parameters, so let me stop this for now. Okay, if you have the API key, then you'll be able to use this Hugging Face trainer function. Else, you'll have to write your own function.
Hmm.
Okay, but
Yeah.
let's say if you're using this, so just look at the parameters. One is the model. Model is the one that we have already loaded. We have loaded the model, right? The BERT, modern BERT model. So
Yeah.
that's input that we are giving here. And next is this training args. So the arguments that we are passing for training that we have already discussed. Then train dataset and evaluation dataset that we have already created, and we have put that tokenizer. Also, we have loaded
So
it.
very different
Modern BERT tokenizer we have loaded. Data collector, you know, right? It is for
padding,
yes,
dynamic
padding.
padding.
Padding, yes. So when you give trainer.train, it will automatically train and your model will be saved. So your model, you'll have to save your model, but you'll have the final model in the variable model. Okay.
Okay.
So now let's say you don't have, okay, you don't have the API key. Then, so these are the various parameters that you need to define it manually. The number of epochs, batch size, learning rate, and weight. The same values have given, just that I have put it manual in input touch. So here we'll have to create our own collate function. So here earlier we were using directly the data collator, but for if you are building your train manually, then you'll have to create this function, collate function. This will do the dynamic padding as I mentioned. Okay.
Yeah.
So next we do the train data loader. Uh, then we load the data. Then the optimizer that we're using is Atom.
Optimizer
So in the
to be
trainer function, it default as a default it uses Adam W as the optimizer. You don't have to mention it. right? We
Okay.
don't have, we
So,
haven't mentioned anywhere.
yeah, here we'll have to define, right? Like if we are using
Yes.
Adam, we'll do it Adam, and if it's Adam W, we'll.
So it's always good that you good to learn, write your own function so that you learn like what is the background optimizer is being used, what's the loss function. So it's always good to write your own functions as well, and that's why it's pretty simple. It's not very difficult. So you can just have your add and w function decided, and then yeah, this I'm just checking. I'll just run this. Sorry, please run this. Okay. Now, this is the training loop that we have written. Okay, so in training, we have 4 steps. One, calculating the outputs. Okay, so first we'll just pass our entire batch to the entire neural network or entire the model, and then we are going to get the predictions. Some values
Yeah,
will be getting the output. So then calculation of loss. So we already have the predicted labels, we have the true labels. Now you calculate the loss using your loss function cross entropy. Yeah, cross entropy. And next is this backward pass. So now you have got your loss. Now you need to distribute this loss across, do the back propagation and distribute this loss across all the parameters. So you
yeah,
will calculate gradients for each of the parameter.
parameters.
Yes. So you will calculate. So in this particular backward propagation, you calculate gradients with respect to each of the parameters. So once you
Mhm.
have the gradients, you know the formula for optimizer, and then we do the we run the optimizer and then update the parameters.
Parameters. Okay. Yeah.
Yes. So once you're done, then the same process, now you're adding up the losses. So total loss is nothing but the entire loss on entire data set, not for just a batch. It's for the
Okay.
entire data set. You will calculate
It's
the
for
loss.
an epoch, you mean?
Yes, it's for an epoch. Exactly.
So I have a question. Like, I mean, we are training this. How do we make sure that our training is going well?
Hmm. Yes. So yeah, first we'll just loop it, and then we also we just make a note of our losses as well. So
Mm-hmm.
here when I ran it, just running it again, it will take a bit of time. So we'll git run. You will. I'm just making a note of various losses that I'm getting for every epoch. So I have put 10 epoch sites, so 10 loss I'll get, and then
Okay.
I draw a learning curve. So this is
Okay.
basically the reduction of our loss that is happening for every epoch, across epoch.
Yeah, we see that the loss is reducing for each epoch.
Yes, for each epoch. So you need to make sure that this isn't zigzag. The loss
Mm.
cannot increase, decrease. Okay, it has to
Okay.
be like a monetarily decreasing. Then it seems that your training has gone well. If there is
Okay.
some zigzags, ups and downs, then it means that there's some problem with the training, maybe, or with your optimizer or with your loss function.
Okay. Then we'll change the hyperparameters and
Yeah.
rerun and check
Yes.
if everything is going well.
Yes, yes. So if you see, yeah, the
Loss
training has
keeps
done,
decreasing.
then you'll see the loss was decreasing, and then let me run this. Okay, so this is the loss. So training logs are for if you're using a train parameter. I mean, the train function for Hugging Face. If you're using Hugging Face function, then I guess
Oh, okay.
logs. So this is we are not using the Hugging Face one, right? We have manually written our loop, so this parameter will not be there. So
Okay.
if you see, and one more thing here to make a notice, this optimizer dot zero grad. Okay, so whenever once you update your parameters based on the gradients that we have calculated during back propagation, you have to reset those gradients to zero. If you don't reset it in PyTorch, it gets appended.
Yeah,
So
I mean, they'll
appending,
get added up, right?
yeah, it gets added up. That will go wrong. Your training
Mhm.
will completely go wrong if you are doing it. So always make sure you make it zero.
Yeah,
Okay.
okay.
All this process is taken care in the train function if you're using Hugging Face, which is easier. But it's always important to learn what is the entire process that is happening while training. That's why I wanted you to explain with manual function itself, manual looping.
Yeah. Now we'll realize why things are happening.
Yes, yes. So now I'm saying the model. I've already built my model and I have my tokenizer. Now I have saved it. So if you go to drive, I'm saving it. Yeah, it's already there, but I think it will get replaced.
Okay.
So, okay, once it's saved, the next part is inference. So now how do we make the predictions? The same way, we load the model and then do the predictions on top of it, right? So let's go, let's move forward. Yeah, okay, it has already saved. And if you see, you'll see all the files that we had earlier. The config file, model tensors, tokens, tokenizer, tokenizer config.
Okay.
All the files that we have seen in the GitHub, we have all these files, all the files that are important to load a model. So we have saved it. So if you see now, the number of trainable parameters will be same for my NER model as well as my for my modern BERT. It will be same. It won't be different because I'm
Oh,
not. It's not like LoRa adapters. We add a layer over it, but here we're not adding any layers or nothing. This is the same exact model. So the
okay.
size of the model will be same as the old one. Just that the numbers, the parameters have, the numbers have changed, the weights have changed, or the biases have changed. That's it. But
They've
we are not
been
adding.
tuned for this specific use case.
That's it. These are being tuned for this specific use case. So the size remains the same. The same 395 million parameter model is what we have built. So there's no change. Okay. Now the inference part. So I'm just loading my model. So the same path. It's the same way as I was loading the modern BERT. The same way we'll have to load. Just that you need to change your path for the tokenizer and the model. So now you Yes, so this is for predictions. So let's say I am giving cats are lazy. So as I mentioned earlier, for tokenizer, we can either give sentence as the input or the list of words. Since I was giving I have trained it on list of words, I have to give list of words here.
Yeah.
Okay, I can't change it. If I'm changing, then your accuracy will drop. So always try to keep it consistent. If it's not possible, then it's okay. But if it's possible, try to keep it consistent. Then
Yeah.
I've just converted into IDs. So these are the tokens that it's been tokenized to. Cards are lazy is being split into two tokens. And then finally, these are the predictions that it has done.
Oh,
So
I
you can
think
ignore
something's
first
wrong.
one and last one. Yeah. Cats is animal, correct. R is wrong. Lazy is wrong. So it hasn't done a good job because do you know the reason?
I mean, like the training set is very small, so you can't expect 100% accuracy with this 200 training
It's
set.
not even 200, 150 only we have trained.
Yeah, yeah, exactly.
With a smaller amount of dataset, don't expect great results from BERT. Try to keep your dataset large. Or and also let's say let's take one thing. Okay, next page. So last 10 we have considered it as a test dataset, right? So let's take from the test dataset itself. Okay. Okay. Since this I'm giving it directly, I don't have to split it over here. Okay. First and last you can ignore. The okay. Tiger is animal, correct. All this is others. And then two is dog. It's correct.
Yeah.
Right. So yeah, when cats are lazy, the problem is we have trained on cat, but we haven't trained on cats. I guess that's the problem. Okay. Even then it's unable to give somehow because it's not trained on larger data set. That's the only problem there. Okay. It's not trained enough. Okay. Then next is this. I've just put a. I just beautified the output. So here you saw, right, like each and every token needs to be mapped to a label. But lay L and lazy. So there is a word lazy, and then that can be mapped to. There are two. It's split into two tokens. So now we have two labels for lazy. So there is a possibility that we might get two different labels as well. Let's say I've got three over here for AZY. I've got two, right? So three and two are very different. So now
Yeah.
when I try to let's say word level labeling when I'm doing. So there we have to take few assumptions. I'm just taken the assumption that whatever the first token's label is, I'm considering the same label for the entire word, irrespective of number of tokens it is. So if L
Okay.
is has three as a label, lazy will has three.
Okay.
Irrespective of AZY, if it has two or one, I don't care. But if the first token is my the token of the entire word will become the token of the will become the label of the first token. Okay.
Okay.
So with that assumption, I have written this code, and you can see. So yeah, so my monkey likes banana. So banana is a fruit. That's right. Likes is others. Correct. Monkey is animal, and my is correct. So this has given correct response. So it depends. You'll have to create a test set and then test it for your accuracy. So few things
And
it does.
also,
Mm.
I think, yeah, the sentences should be similar to the test sentences should be representative of the training
Mm.
set. If you'll make some very different sentence, this will
Then
obviously
it.
end up giving wrong answers. See, here in the test data set, we have dog likes mango. And
Mm. That's the
here,
reason. Based pattern, it's able to be even the monkey is not trained.
yeah,
But if it's very different, then it might fail. So that's the reason, like for BERT model, no, since it's 396, 395 million parameters, it has to change. So your data set has to be large enough. Okay.
yeah.
Then next is this evaluation. So let's evaluate on our test data set. That is the last 10 samples. So this is just the code for doing the predictions. Mapper is not defined. Okay. Let me check where's the mapper. Okay. Hmm. So I have just taken the references. References are the two labels, and here I have done the prediction, get prediction, and since I was getting the output as this, like others, animal, I have just converted it into numbers because our NER tags are in numbers, right? So that's why I've just changed it, and then have have created the key classification report using scikit-learn metrics module. So yes, these are the we have got 100% accuracy, but yeah, it's just because the data set is representative that's why we are getting. But ideally, it can go wrong with a lot with a small data set. So yes, this is the end of the fine tuning activity for NER use case. Any doubts?
Oh, nothing as of now, but it will be interesting if we'll test out use cases with a large data set. Like we
Mm,
definitely need to have a huge computing capacity, but yeah, it will be interesting to see large data sets being trained.
yes,
But the
yes.
process won't change, right? Like be
Yeah,
it
process
small
is that.
data set or a
Mm,
huge data set, this is the code that we are going to run. All that changes is the size of the data.
exactly. Only the size of the data changes. The rest everything remains as it is. So yeah, we'll be able to share this notebook as well, so you people can run for your own use cases and then test it out.
Yeah. So that's all for this video. If you have any questions, please do put them in the comments. We'll answer. And for more videos on fine tuning, follow this fine tuning series. and we'll be adding more use cases and applications.
Yes. Okay, guys. Thank you so much. Bye bye. Happy
Bye.
learning.
Happy learning.